Hello and welcome to our bonus session. I thought I'd talk about a couple topics today. I'd start off with a discussion around Anaconda, Python best practices, and then I'll move on to Anaconda environments or environments in general. So the idea here is to talk about topics that are relevant within not just this course, but the broader arena and the discipline. So that's the basic idea of talking about things like the things like error handling and logging, and then also separations of concerns, important regardless of what you do in pretty much any programming language, but definitely relevant whenever you're doing data science and using things like Python and so on. So a brief agenda, error handling and logging, separation concerns, and then acronyms. Then I'm going to shift over to a different presentation and talk a little bit about environments. So error handling and logging. So what's the point? And is always a good question. The basic idea here, and the reason that you should care, is that you will encounter errors. You're dealing with an interpreted language. You are evaluating the code during runtime, not during the compilation stage. So you're going to have a higher number of errors than you might have in something where you have a compiler essentially pre-processing your programs and removing and detecting, detecting, not removing, you do the removing, detecting any kind of errors that are syntactical in nature, so that you are left only dealing with basically logic errors. Runtime errors are those things which occur as the interpreter sees your code and tries to make sense of what you're trying to do. The idea is to avoid bad things from happening in an uncontrolled way whenever those sort of situations occur. There's several reasons that you can encounter errors and challenges within your code. Some of them are within your control, such as your programs that you write. The others are going to be inside of the data that you're processing and interacting with. So it's important to be able to attempt to handle those things as well as you can. Python has an approach of assuming that everything is going to work out pretty well and then handling the exception case rather than attempting to avoid it entirely. Different philosophical sort of approaches, but that's the more Pythonic sort of approach is let's just go for it and then handle the situation when it doesn't work out. But more importantly, regardless of the situation, if something negative occurs, you don't want to ignore it. You want to know that it occurred, when it occurred, and so that you can address it and fix it. Data is inherently dirty whenever we're doing the work that you do inside of data science. So you will encounter situations where something is not of the format that you're expecting. Parsing of it will not succeed. So you want to be prepared whenever that does occur. One thing that you can do, this ties in to some extent around tests and doing test-driven development, but assertions are a way of basically making a statement of what you expect to be true. It's a way of defining preconditions that you expect. This is what I'm expecting whenever my program runs. If something is different than that, it's outside of the scope of what I prepared for. So rather than attempting to handle everything, you say, I expect that there's a length in the string that you give me. If there's not a length in the string that you give me or array that you give me, then I can't do what's necessary to do. So if you're calculating the average of a series of numbers and you're not using the built-in function for whatever reason and you pass in a zero length string, division by zero is undefined, so you don't want to attempt to try to do it. So rather than raising some less than desirable error, you want to catch something earlier. Another thing that you may want to do whenever you're dealing with data is to handle the situation where values are missing. So there's oftentimes holes in your data. There's several ways that you can address those holes. One of them is to remove the records that contain any gaps. That's one approach. Perhaps not a best choice, but it is a choice. Another approach is to replace them with a good approximation. So maybe you take the average of all the other values and insert those instead. Or maybe it's more intelligent. Maybe it's average of things that look like it or act like the record that has holes in it. And so it is something that has to be purposely decided. You don't, and it has to be well documented. The fact that you say that null values were addressed by replacing them with averages may be appropriate, but it needs to be clearly communicated to whoever it is that's interpreting your results. One thing that you may want to do is use try except blocks, and these are basically exception handling. So the idea is that whenever something occurs that generates an exception, which is something that is unforeseen, that you catch that exception, use an exception block, and do something with it. And you should only be able to attempt to accept something you know what to do with. Generally speaking, you want to catch it as close to the thing that's causing the issue as you can. You want to oftentimes raise the exception that occurred, so essentially accept it back out so that something else can see it as well after you've done something, that if you can do something with it. You, generally speaking, want to save the fact that that occurred and logging it to something, and we'll talk about logging here in a moment, so that it can then be addressed in a more systemic way. You may want to retry depending upon the situation. Oftentimes with a lot of our especially cloud-based processing platforms, exceptions are part of the domain. But what you do is when they occur, you don't just give up, you try again, generally speaking, after a random amount of a delay. Generally speaking, you introduce delays of a random duration in your retry strategies, primarily so that you don't end up either indirectly creating a stress test, which can occur, or being in contention with some other activity, so that you both pause the same amount of time and both encounter the same situation again. So if all the parties involved, be they processes, essentially pause for a random amount of time, or pseudo-random as the case may be, and then try again, then you're less likely to encounter the exact same scenario. You don't generally want to display the call stack, and a call stack is basically the list of the functions, oftentimes with parameters that are describe where the error occurred, because displaying that can potentially be a security vulnerability. And generally speaking, don't just catch everything and do nothing with it. It is possible to do. You can do a catch and then a pass, or sorry, except and a pass in Python. And basically what that does is eat any exception. So you never see any exceptions, but that doesn't mean they're not happening. You're just ignoring them en masse. One of the other things you'll want to think about is logging errors. It's relatively straightforward to do. The idea here is that you want to allow visibility into your programs so that you can tell what's going on. This becomes more important as the programs become more robust and more complex and have multiple components and phases and stages and pipelines perhaps. So in those sort of situations, you want to be very cautious of ignoring what's happening. So you want to detect that something's occurring, and then oftentimes inside of your exception block, or maybe inside of an error checking set of code, be able to log information appropriately. To that end, there's a library called logging available to you, import logging, and then basically you tell it what to do. So you do a certain amount of configuration of where it should log to. And then there's this concept of a verbosity level, so that it controls how much is written based upon the type of things that occur. So the idea is that you have the ability, oftentimes set inside of a configuration file or something, so that you can turn down the amount of logging you're getting if everything is going well. And then if for some reason you're encountering situations where there's something that's occurring relatively frequently that isn't desirable, and you think it's going to happen, then you turn it back up. So you turn from just displaying errors to perhaps you start displaying debugging information. And so the downside of being conservative on what you're recording with your logs is that something might occur that you don't get the detail that you need to determine what happened. The trade-off is, though, that you're potentially logging a lot of information that's not necessary. So that's kind of a thing you balance along the way. Looking again at some additional details on logging, this shows the concept of setting different levels of verbosity. So in this case, I'm setting the format to not set, so logging.notset, and that basically says log everything. So you can see then that the logging is writing literally everything out to the text file that has been created. So log files are oftentimes used in multiple environments. Sometimes you'll utilize tools that are a bit more advanced. There are services like Azure Monitor that allow for not necessarily textual log filing, log recording, but more event recording. And so you do the same basic thing, but it's in a more robust, highly reportable, highly transactional sort of environment that allows you potentially to do correlation across multiple services. so that you're able to detect that all of a sudden all of these certain types of services encounter the exact same error. Most likely that's environmental in nature, so that it's very beneficial to be able to look at that sort of stuff. But the key concept to take away is that recording things that occur is an important part of what you want to be doing when you're writing a program, so that you can figure out what went wrong, and you often plan for what went wrong. Separations of concerns. The basic idea here is to do one thing and do it well. So generally speaking, you want a program that does one thing, and that's literally what it does. Maybe you have a library that focuses in on one set of things that correspond around a very specific set of activities and domains. So the basic idea here is that you don't want unintended consequences of changes to code. That is the thing we're trying to avoid. That's the whole point of this sort of concept. So you have sections of codes that do one thing. Generally those sections of code are libraries or methods or maybe in a file. And then they shouldn't have a high degree of interactions with other things unless it's through something that is essentially an interface. So a rigid way of communicating between services or libraries so that you don't know too much about the thing that you're talking to. So that's where this concept of using classes comes to play, is that the class exposes a set of methods that it knows how to do, and you don't really know how it does what it does. You just know how to talk to those methods. Same basic concept with an interface. You don't want a class that does everything. So that's the kitchen sink class. Something that literally does any sort of utility helper thing, whatever it might be. You want them to be highly cohesive so that they all kind of go together with a very well-defined purpose, and you want to minimize the amount of coupling, that's the dependencies between those sort of elements, so that you don't have that inadvertent dependency and that inadvertent consequence of changes that you don't foresee. And in general, don't copy paste code. It's a bad idea to start down. You probably know this. Instead, pull the code out, put it into either functions, classes, or something else. Basically use forms of abstraction and do that instead. So some acronyms that you may want to live by. I borrowed this and I'll give the reference here in a little bit. It's clean code in Python, I believe. So basically don't repeat yourself, and once and only once. That is kind of the clever ways of saying don't copy paste code. The reason you don't want to do that is if you have the same thing over in multiple places, it needs to be fixed in multiple places. That means that you may also have diversion of those various branches of the code that occurs, which will increase your maintenance costs because you're having to maintain in copies of the same basic thing with minor differences between them. Generally speaking, that ends up with something that's unreliable, so that you're going to potentially have errors that are occurring that is not predictable, because it looks like it's all kind of the same thing, but it's subtly different. You ain't going to need it. So YAGNI is basically avoid over engineering, and this kind of applies to the concept inside of agile development of minimal viable product. It is building the thing that is the least sort of implementation that you need to address the issues that you're dealing with. So don't build it because it's cool. Don't build it because you think you might need it. Only build it in response to a stated requirement, and only doing so in a way that meets the stated business need. Keep it simple, always a good idea. And Occam knew what he was talking about. So basically, you want to be following the simplest viable solution is probably the best one. Look before you leap, and check before trying things. Similar sort of concept in this, basically avoiding exceptions. Not necessarily Pythonic, but it is something to consider. And there's two schools of thought. One is, if you can tell that it's going to be an error, don't encounter the error and then handle it. And you definitely don't want to be using exception control for flow control. Those are bad combinations of things. Also very slow and just kind of sloppy. Generally speaking, you balance between the two. If you know that there's a chance that a column will be empty, checking for empty columns makes total sense. If something is empty, then it makes the entire record not be usable. Appropriate to go ahead and exclude it during the pre-processing phases. But you can't always handle all errors that might going to possibly occur, so you instead handle those exception cases with try and accept. Write code that performs an action directly. So rather than trying to handle all the things that may get in the way of it not working. And that's kind of the Pythonic approach, a little bit more than that look before you leap sort of concept. But again, it's a balance between those two extremes. Some resources you may want to consider. Pretty good reading there, so do take a look. Now I'll go ahead and jump over to another presentation and run through it very quickly. And this is around Anaconda and Conda environments. So as we've talked about before, Anaconda is a distribution, a packaging set of Python and related technologies, kind of an analytics environment that's easy to get up and running, right? So within that, it has this concept of an environment. So an environment you may have bumped into already. Whenever you go into Anaconda Navigator, you see it. But the basic idea of an environment is it's nothing more complicated than a folder. And it's a set of folders in particular that essentially describe a working space. And I'm trying not to use the word environment, but it's a place where you know what's been installed inside of that, what libraries are available, and so on. And it's for a particular purpose, generally speaking. And it allows you to do separate things, like have a particular version of Python in one environment and a different one in another, because the libraries that you're using in that other environment may require a certain version. Whenever you do an installation of Anaconda, you get the base environment that's in there out of the gate. You can then augment it with additional environments yourself. To create an environment, there's multiple ways to do it, but you can do it through the Anaconda Navigator by basically going in, click on the Environments tab, click on Create, pick what you want to be available to you inside of that environment, including what version of if it's Python, if you want maybe 3.7 for some reason. You can also have R available to you. You can also do this potentially with additional other languages that you may be using, such as Julia or some other language. And what this is doing, whenever you do this clicking, is it's actually going out and creating a folder and setting it up with an initial implementation. Understand, though, if you do environments, not everything is going to be inside of your data wrangling environment that is in your base environment. That's kind of the whole point, is that it's a subset of stuff. So it'll start with kind of a minimal set of packages. You'll want to change it over time and install additional ones if you go that route. You can also do so through command lines. You can do conda create environment or conda environment create. I'm not showing you that here, but it can be done. Oh yeah, I am. So conda create, and then give it a name for the environment you want to create. And it basically will create it, no spaces or in the name. And this allows you to basically go out and create an environment. Similar concept to doing it just as we've done other things with both the command line and inside of the UI. Equally viable. Sometimes it's easier to do things at a command line because you can script them out. So you select an environment by activating it. That's the key concept, conda activate in the name of the environment. And also, generally speaking, whenever you create a new environment, especially through that UI, it shows up inside of your start menu, inside of the parentheses, so you can go in and start it from that particular domain. Type of issues you may encounter whenever you're dealing with environments is that it may not have the libraries that you think are there. So don't assume that just because you were using it a minute ago and you switch environments that it's going to be present. You may end up needing to install some additional libraries. Potentially are duplicating space that's going on your drive, but that's not a huge deal. And you can script your switches between environments, as well as scripting the creation and population of whatever libraries inside of those environments as well. Again, these are things that you, as a data scientist, will likely be wanting to know how to do. File this away for something that you may want to take a look at later on. It may not be relevant right now, but later on you'll be wondering, how do I do those environments again? So you'll at least kind of have some sense of what I'm talking about. Some additional resources that are available. If you Google managing Conda environments, you'll find some pretty good resources. So takeaway, they're basically folders. They allow you to do specific versions of specific library and or softwares whenever you're doing development. You can switch between them relatively easily. You can get a little confused sometimes of which one you're using and which one's installed where. But whenever you're potentially dealing with like open source software, oftentimes the first step is create an environment. So with that, I'll go ahead and wrap this up. Stay safe, and we'll speak again on Wednesday.